welcome back, and it's a pleasure to welcome back Mohammed Abouzaid in his third lecture in this series, and he'll talk about Bordism of derived orbifolds. Please.
Thank you very much. Thanks to everyone for being patient and being willing to come back. Thanks to the Field Institute for the invitation. So I will give my last lecture. I want to start with some addenda from what I said this morning. The first one is that just like in the first lecture, these orbifold Bordism groups are in fact homotopy groups of spaces. Of a space. And this space can be constructed exactly like I did the first lecture. And that is why I gave the first lecture that way. And I highlighted this point so that I wouldn't, because if I do it here, if I did this morning, it would have taken 20 minutes. And now I can just tell you whatever I did in the first lecture, you combine it with the ideas of the second lecture, and you can just produce the space. And that is, of course, only the beginning, because this is a homology theory, so we expect not just a space, but collection of spaces, something called a spectrum. But once you have this idea, this is the key idea of how to get started. That's the first thing. The second thing is that I suggested that somehow we don't know how to compute this group, but actually this one we know how to compute. Okay, this is the monoid Z isomorphism classes of finite groups. Okay, and I should say what I mean by that. This is really bad notation. There is the obvious relation, which is, if you want to think of it as a ring modular the relation that the class of G1 times the class of G2. G1 times G2. So that's the relation that you have. So, but beyond this, there's basically nothing. I mean, the second one. So actually, you can show that the first one is trivial. Complex Bordism of in dimension one. Bordism of complex orbifold in dimension one is trivial. It's a slightly non-trivial computation. And then for surfaces, there are some sporadic results, usually in what is called the effective case. So the effective case, so for effective orbifolds, and effective means that the general point has trivial stabilizer group. There are some sporadic computations in the literature, but already in the ineffective case, which is what's relevant for the things that I'm interested in, we don't know in dimension one, in dimension two. But I think it's doable. I think it's doable by hand. I think it's not at all a mystery. Okay, so that does the addenda from this morning. Okay, so now I want to talk about derived orbifolds, and then to do that, I have to explain to you why you would care about derived orbifolds, and that's because at some point in the morning, in the motivation, I did a little, sleight of hand. I somehow didn't quite. I was not fully honest. So recall in the morning that we justified orbifolds, studying orbifolds by looking at maps from some Riemann surface to some target, okay, and saying that we want to look at the moduli space of such, and the moduli space of such should have an action. So the space of such should have an action of the automorphism group, and the moduli space of such should somehow be taking the quotient. So which automorphic, and that we should considered up to automorphism. Okay. And the reason that you don't do things equivariantly is because you really have to let the modulus vary. So the issue, so I said, well, so that means you expect to see an orbifold. But actually, if you think about it, what I said is that you should try to model this as having some base manifold, and it has a group action, and you have a vector bundle, you have the group action, equivariant vector bundle, and then you have a section. Okay, and then the space of solutions, the moduli space that we're interested in is, so let Z equals S inverse of 0, and then we look at Z mod gamma. Or really, I want to do this, but okay, let's just look at Z with the action of gamma. Now, the problem is, if when gamma is trivial, in the usual manifold case, you can just pick S generically so that this is a manifold, okay? But in the equivariant world, transversality may fail. And to understand what is meant by transversality may fail, you can just describe everything locally. So locally, it turns out that in the locus where gamma acts freely, there's no issue. The issue is exactly at the fixed point. So at a fixed point of the gamma action on M is described by some representation, by a gamma rep. Let me call it V plus. And the fiber of this equivariant vector bundle is some other representation. And E is described by another gamma representation. Let's call it V minus. And the data of this map S is an equivariant map. Sorry, just use the same S. Is an equivariant map from V plus to V minus. It's not a necessarily linear map. What would it mean to be able to achieve transversality? Well, it would mean that if you pick any point here, you can choose this map so that it's differential. So this map so that its differential is generic. So for example, if the rank of this is bigger than rank of this, and you want to make sure that at the generic point, differential is surjective. But just finite dimensional representation theory prevents this. So the existence of non-isomorphic irreducible representations, non-isomorphic prevents the existence of enough maps to satisfy transversality. So you should have in mind, e.g., just the simplest case, or maybe not necessarily, but gamma could be the cyclic group of order 2. And then one of this could be the trivial, and the other one could be the non-trivial representation. And then the only way to have a map from the non-trivial to the trivial representation is to do Z goes to Z squared. So plus C with non-trivial action, and minus C trivial action, and then S must be Z squared plus higher order term. Well, no, just do O is equal to fourth. And so the derivative of the origin is always 0. Okay. So that means that while the lecture this morning was about orbifold Bordism for actual applications to symplectic topology. It's really, there are some settings where it's useful, For example, if you want to study, something like Gromov-Witten theory of projective spaces or Grassmannians and so on and so forth, then we can prove that we have orbifolds. But if you go outside of this regime, then you run into this problem, okay? And then you cannot arrange to say that you have an orbifold. This is the only kind of structure you have locally. Then the question is, what does it mean? To have space, space should be put in quotation mark, space, with some local description as the quotient by gamma of the zero locus of this, which is locally described with local structure. That is given by S inverse of 0 mod gamma for exactly such a thing, plus B minus, which is a gamma equivariant. What is a global structure on a space? How to formulate some notion, some global notion, which locally is given by this. Okay, and there are multiple answers. Multiple answers to this question. So the first is due to Fukaya Ota Ono. Maybe I should say due to Fukaya Ono around 98. They call such a thing a Kurnishi space. And I do not want to elaborate on what it means to be Kurnishi space, but it's basically have the structure near each point, and then you have some change of coordinates which allow you to both change what the vector bundles are and what the vector spaces are, what the representations are, and change what the group are in some ways that are compatible with each other. But it is extremely cumbersome. Okay. And since then, there's been more homotopical variants. So anyway, okay. But what I want to do is I want to present some approach that is the one that I've been using. I'm collaborators and I've been using in symplectic topology. It's again justified by a result of Parton. Okay, so I will use in this board, I want to use some vague words. Okay, so another formulation that you may want is as zero section, zero locus of an orbifold bundle over an orbifold. And since this morning, I didn't want to define what an orbifold was. And this is what you may want to call a derived orbifold. Okay, and the idea is that the derived direction is the direction of the bundle. The way that I think about it is, if you have a manifold, if you have an orbifold, there is a tangent space, and the vector bundle that you're putting in is going to contribute to a negative direction of the tangent space, and that's why you think of it as being derived. Okay, but in the formalism of this morning, we can present every such object as a quadruple. And I know I'm being very abstract, and I'll try to be concrete in a second, as a quadruple. So the quadruple consists of G, X, E, and S. And this is, again, a compact Lie group. This is a space on which G acts. This action has finite isotropy. finite stabilizers, exactly like this morning. This E is a G bundle. Sometimes I call it T minus, but today, not today. And this is a G equivariant section. Yes, sorry, G equivariant vector bundle. Thank you. Vector bundle, and this is a G equivariant section. And so it's a lot of data. It's even more data than this morning. But it's, again, some data that is not too hard to explain what it is. And it allows us to tie to constructions in equivariant topology. So the first thing that I want to say is that the reason that among the reasons that I favor this construction, by the way, X is finite dimensional. Among the reasons that I favor this formalism is that I proved the theorem with McLean and Smith. I referred to this earlier. One that essentially says moduli spaces of holomorphic curves on symplectic manifolds can be naturally equipped with this structure. Okay? It's not something that comes out of some abstract machine. It's something that comes out of some geometry, from differential geometry. And we don't have time to give the details, but there exists a natural construction. Let's say natural construction of such a structure of what do we call it? Of such a global presentation. Global presentation of moduli spaces. Of curves. And we did genus 0, and then later higher genus was done in symplectic manifolds. So not only do I find this convenient because it uses mathematical notions that are not too elaborate, but it also happens that when we do geometry, when we're actually thinking about Gromov-Witten theory, which I said very little here, that comes out as the output of the construction. And because of this theorem, because we produce something of this nature, one doesn't have any more to worry about how technically difficult the theory of Konishi spaces are. And basically all the other alternatives were just as, if not more difficult. So this makes life much, much, much simpler. So let me discuss some basic notion. So the first thing to say is that in this setting, you want to remember you don't really care about this X itself. So I never said that this X is compact. So if you have this quadruple here, you can call it, let's call it a global presentation for a derived orbifold, but I don't want to keep saying that. So in this lecture, this is just what I mean by derived orbifold today. Okay. That's what I mean today. But if I want to be precise, I will say global presentation. Okay, so you want to know what it means for such a thing to be compact, because when you build cobordism group, it's important, you always build cobordism groups out of compact manifolds, compact orbifolds. And I don't know how to do it assuming that X itself is compact. So the actual definition is that a global orbifold is compact if this zero locus is compact. You say that derived orbifold compact if S inverse of 0. Again, this is what I call Z. But let me just do it. Mod G is compact. This is what you care about, and what's happening outside is not something that you are interested in. And so this means, for example, if V is a gamma representation, then you can consider the following example. So So you say, so when I write gamma, I usually mean finite group. You can consider the example of G equals gamma, and now X is going to be just a point, and E is going to be the gamma representation itself. Okay, and then I'm going to put some section S here, but this section S is just the, I'm just write section, but it's not a, I mean, you can say it's a section, it's just the inclusion of the origin. It's just the inclusion S of the point, origin. Okay, and this is the first, I would say this is the first interesting derived orbifold. I mean, that's not an orbifold. I said earlier that I think of this vector bundle as some kind of negative directions in the tangent space. So this object has a virtual dimension, which really we should just call it dimension, but for now I'll call it virtual dimension. It's given by minus the dimension of V. Okay. So unlike the Bordism groups of orbifolds, which are supported, and the manifolds, which are supported in non-negative degrees, this may have stuff in negative degrees. Of course, you need to prove that. I haven't yet introduced what Bordism means. You'd have then to prove that it's non-trivial. Okay. But as a candidate, there's somehow definitely a candidate. Okay. You can make, of course, slightly more elaborate constructions involving by replacing this manifold by this point by some manifold and V by some vector bundle on it, and that will give you something more complicated. So that is actually what Pardon proved. So this, the fact that these two things are equivalent is Pardon's theorem. Thank you.
What is the virtual dimension in general case?
Virtual dimension is the dimension. So thank you. I can just do it. I can just do it here. So general virtual. I just want to say virtual dimension of this triple G X E S. Well, S is not relevant. Is the dimension of X minus the dimension of G minus the dimension of A. And the way that you check that the formula makes sense would be if you were to achieve transversality, would it be the dimension of the zero locus modulo G? That's what you want. Thank you. While I'm here, I want to ask a question. Oh, no, can't ask it yet. So let me just get to it in a second. So now the awkwardness of this formalism is that there are some equivalence relations you have to impose. Now, actually, in this case, you have to impose an equivalence relation anyway. So, I will. So there is a notion of equivalent. There is a notion of equivalence that extends the one that we had earlier. So we say that. Okay. So again, unfortunately, a lot of notation, but 0, E0, 0, and same thing with 1. 1 equivalent if there exists a map, so a bunch of maps, and they'll all be called F. So G0 goes to G1. This is a group homomorphism. X0 goes to X1. This is a G0 equivariant map. E0 to E1. This is a map of bundles. If you don't like it, you can just do like this. Pull it back. It's a map of G0 bundles over X0, and then you would like this diagram to commute. So commuting with F, commuting with S. S0 and S1. So there's two sections agree. And now, last time, when we defined equivalence of orbifolds, we needed to formulate some stuff. And now you're going to do the same thing, such that one induced map on 0 loci modulo G0. This is an S0. This one is homeo. Exactly what I had earlier, except I don't say it about the total space because I don't care about the total space. I care about only the 0 locus. 2, along the 0 locus, the map of stabilizers is stabilizer groups isomorphism. So stabilizer groups isomorphic along the 0 locus. And then there's this condition, some condition on tangent spaces, which I want to write down. Because it's a bit hard to guess at first. And then once you see it, it feels very natural, which is that the following sequence. So this is the Lie algebra. From G0 to G1, there's a map of Lie algebras, G0 to G1. Now, the Lie algebra of G0 maps to the tangent space of X0 because, well, it acts on it. So there's vector fields. It gives you vector fields. Now, the same thing for Tx1. Okay. So this map here is both the G1 acts on X1 and X0 maps to X1. Okay. Then now X0, it maps to X1, but then it also maps to E0 by this section. And finally, this maps to E1. This sequence is exact. So this condition is a little bit surprising at first. I don't know, maybe it's not clear what it means. So let me give you an example. The easiest way for me to give you an example is to let the G be the same. So example of an equivalence that's not of the type we have before. So fix G and take some Gx Es naught S, and now consider another vector bundle. Another vector bundle. Let's call it E prime over X. So what I'm going to do is I'm going to produce for you an X prime, an X1 that is equivalent to X and that has some interesting information in it that somehow that displays some non-trivial equivalence. And so then you can just take G, and then you can take the total space of E prime. Okay, it's total space as a vector bundle, and on this total space you can take E direct sum E prime. Now I'm abusing notation because really what I should do is I should maybe write pi for this projection, and I should pull back. Okay, would that help anybody? Maybe. I should pull back. And then there is the pullback of S, direct sum, basically the identity on E prime. So this is another section. What is this doing? It's some very general construction, but it does the following thing. For example, if you start with a point, then what this tells you is that if you take a vector space, and you take two copies of it, and you think of this one as the base and this one as the fiber, and if your section is just the identity map, then basically the identity map cuts out the point transversely. So you consider the map from a point to here as an equivalence. Okay. So that's how, this is the basic case. This is what the basic case most easily generalizes to. This is when you try to combine it with a bunch of other things you could try to do, like changing the group and changing the vector bundle, maybe even to just take just open embeddings, because you don't, the structure it doesn't really matter. Over here, it doesn't need to be the identity. It just needs to be something. It can be whatever it wants, because we need to focus just at what's happening along the zero section, and writing it just about as a condition on tangent spaces achieves that. Okay. So this is the notion of equivalence. And now I have a question, which I don't know the answer to. And if I knew the answer to it, some things, I mean, I'm not sure that some things would be easier, but some things would be conceptually easier to explain. The question simply is, is every derived orbifold equivalent to one, to an orbifold for which x0 is compact? Up to equivalence. Can we assume that x? There's some reason that I'm asking this, and the reason has to do with this annoying s that I keeping track of. Okay, this s, what it's really doing, it's trivializing. So x, as you see by the stabilization, is not compact. Need not be compact. So, in order to make sure that you have some well-defined invariance associated to it, you have to specify something at infinity. And that's what this section does. But if we could prove something like this, then we can probably give a definition that doesn't rely on that doesn't necessarily involve the section F. But anyway, so that's a question that I don't know the answer to. Oh, yes, I'm sorry.
I'm sorry, but I guess this is the question about the way you define orbifolds. So we assumed that it's compact, and like the whole point of this result of Bardon was that we have a compact presentation.
No, but even if you take the other perspective, if you can just say, if I give you an orbifold and an orbibundle on it, and you have a section, and you formalize some notion of equivalence, you still will need some kind of equivalence, which will allow you to make things bigger, like here. The dimension of the underlying orbifold is not an invariant in this world. So now the question is, up to equivalence, can you ensure that the ambient orbifold is actually compact? Anyway, I'm happy to talk later. Okay. Okay, so that's the question. This is a question I don't know the answer to. And now that we have this, so we can then the Bordism group exactly as in the morning. And the essential thing, as before, is, again, I'm going to draw some schematic thing. So here there is some x01. Oh, that was a g01 first, and then e01, and then s01. Okay, and it has two boundary strata. Okay, I'm going to be tired of this, so I'm going to use some kind of blackboard x01 for this. Okay, and it has two boundaries. This x01 has two boundaries. Boundary x01, boundary 0, and boundary 1. And then what it means to have a cobordism from x0 to x1 what it means to have a cobordism is that you take x0, you have an equivalence from x0 to x01, so equivalence. And then you have x1 to this boundary stratum. You have x1, you have an equivalence from this. Then you have a cobordism between the equivalences. Okay. And yeah, again, if you sit down and try to figure out how in the world would you glue these things together to show that this is an actual equivalence relation, you will find that you'll need to appeal to the hard part of Pardon's theorem, which is basically about extending vector bundles on orbifolds. Okay. So that defines a group. This defines something which you could call the derived orbifold. So D is for derived orbifold. So Bordism is here. This omega basically means I'm looking at oriented things, but in my case it's complex orientation. And okay, and this is the virtual dimension. Questions? So this has a map from the orbifold Bordism group. Okay, and therefore a map from the complex Bordism group. And the things, yes.
Explain that again.
This, yes. So this stands for oriented Bordism. So in these lectures, it means complex oriented Bordism. This means it's orbifold. This D means derived because I added this thing. And this K is the virtual dimension. Okay? So I described what the virtual dimension was. So this splits, if you go through, I mean, maybe the first thing to check is that my notion of equivalence, most importantly, this sequence here that I wrote down, okay, tells you that the notion of virtual dimension is invariant. Okay? And you can just see it because, well, there is x0 here and e0 and g0 here, and there's x1 here and g1 and e1 here, and this is exact, so the dimension is exactly as expected. So this one is the universal object in which invariants that come from symplectic topology are valued. That's basically the point. Gromov-Witten invariants are valued in this. But we do not understand it well enough to go beyond that. It's very difficult for us to do algebra with it because we don't know its structure. So the first question that I don't know the answers to, what is the group in degree 0? I don't even know that question. So in the case without the derived things, you could explain everything. Okay. With the derived thing, I don't know anymore, and the reason that I don't know anymore is because here's some class that I don't know how to express. So it's pick a manifold of dimension, let's say 2k, that doesn't bound, it's stably complex. Dimension 2k, call it just M of dimension 2k, and an irreducible representation. I mean, I'm quite sure this class that I'm about to write down is non-zero. An irreducible representation V of some group of dimension 2k, same thing. It's complex, but I'd say complex representation. Let me say dimension k, complex of some group gamma. Now just take M times this thing that I said earlier, gamma point E, and then the 0 map. Okay, this has virtual dimension 0 because I just made it cancel out. I think we can probably prove that this class is not trivial, but I'm just saying this to indicate how complicated this thing might be. Now, is this all? Probably not. So how much more complicated is this ring? So it doesn't feel like, because it has classes in negative degree, it doesn't feel like a ring that you're going to analyze by working up inductively by dimension. You have to probably work inductively with some other inductive scheme, probably having to do with the complexity of the representations that arise. Now, what is known about it? Well, the things that I said this morning, the homomorphisms that I mentioned this morning are basically all known to extend. That's the surprising thing. So in symplectic topology, there is a theory, something called of virtual fundamental classes. Fundamental classes. And what they are in this language are homomorphisms from this ring to, well, other rings. So in this language, these are maps. I didn't talk about the product, but ring maps. Full Bordism ring, usually just in degree 0, but I'm just going to put to, well, various things. And this morning I said that this, there is this assignment that takes a derived orbifold and it assigns to it an orbifold. I'm sorry, and it assigns to it 1 over the cardinality of the group, of the stabilizer group. And the point is that that one, the real input, the real hard work that Fukaya and Ono did, 98, is to show that the map that says point mod G to 1 over, I try to use gamma, 1 over the cardinality of gamma extends to a homomorphism. With domain the derived orbifold Bordism. Okay, which means there is some recipe to assign a number to this. Okay, there is some recipe to assign a number to this. I strongly suspect that that recipe is something related. I actually don't know what it is explicitly, so I'm not going to write anything on the board. But the expectation is that it would. Yeah, my expectation is that it's actually 0 because of the way that they construct it. They do something called multi-valued perturbations, so that then you can move this point away from the origin. And I think because this is a product rather than a non-trivial bundle, you should be able to do it just on this factor, get 0, and then that goes to 0. In fact, that's part of asserting that it's a ring map. So this would not be detected by this assignment. Now, the more shocking thing, this is, yeah, good. We're leading into the next part. The more shocking thing is that Fukaya and Ono also proposed that you could do the same thing with the other homomorphism. So, Fukaya and Ono, 99, proposed a method to extend the map from the orbifold Bordism group to Z, the one that takes everybody except the points, the one that takes point mod gamma to 0, and well, to 1, if and only if gamma is trivial. Okay, to this derived orbifold Bordism. And the method is basically back to this thing that I said about, thinking about the failure of transversality. And when I said, when things fail to be transverse, so the reason transversality fails is because you have these two representations and you're looking for a map between them. You cannot achieve, if the irreducible representations are different, then you cannot ensure that the differential is surjective at the origin. But so then you maybe ask if there's a weaker class of maps, not necessarily surjective maps. And then the idea is that you can always use complex polynomial maps of high degree. So in some sense, there is some maximal amount of transversality that representation theory allows you to achieve. Okay, so in this toy case, in the case where we just had Z mod 2 acting on C non-trivially, mapping to C with trivial action, I wrote that a map S is equal to somehow Z squared plus O C to the fourth. Okay, and the maximal amount of transversality in some kind of jet sense that you're allowed to have is this order 2 thing, and you cannot do better than that. Okay, and so now what they propose to do is you can just look at sections, smooth sections, which along the stabilizer, which in the normal direction of any fixed point locus are of this polynomial type. So look, then consider sections which in the normal direction of the polynomial of the singular of the singular set. Have this our polynomial type. And when you do that, you pick one generically, and then you just count the number of zeros away from the singular set. Zeros away. Locus away from the locus where the isotropy is not true. Okay, so this is basically it says, well, you do transversality for wherever you can, and where you cannot do transversality, you make sure that you have some boundary conditions, which is how I think about this boundary condition near the singular locus, which is sufficiently well behaved that you don't have to worry about zeros escaping, which is always the problem. So they showed that this is well defined. So this is followed by succeeded by work of Parker and Bai and Xu. And the reason that I'm saying that Fukaya and Ono proposed something is because they basically did it in a 10-page conference proceeding. It was basically like an announcement. This idea should work, but the formalism that they were working with Kurnishi spaces was quite cumbersome, and it would have probably taken hundreds of pages to take this basic idea that I'm saying here, this basic idea of just use polynomial maps, and then patch it together globally until you could actually construct an invariant in the in the old formalism. From the new perspective, this is really not that hard because you're just going to be talking about everything equivariantly with respect to compact Lie group. That's what they do. Okay, so they formulate this in this kind of global quotient perspective. Okay, so I think for if you'd asked people 20 years ago, which if you ask them, most people, if you ask them about this ring and what is it in degree 0, they would have maybe guessed that it would have some rational parts to it, but it now looks like it's not. It's very plausible that it's in fact just a bunch of free sum ends, but we don't know yet. We don't know yet. We don't have 0. Okay, so that's the relationship between this theory and the ordinary cohomology. There is, you can ask about other cohomology theories. So that's the next thing. So this morning, I said something about some map to K-theory. In fact, I said it about orbifolds, but it's about derived orbifolds. So in this paper with McLean-Smith, we construct. Told as a topologist, I should call it the Todd genus. So the omega orb inverse, and it extends the one for orbifold, and it extends the one for complex manifold. This is classically. Okay, so here this ZZ inverse, I shouldn't write it like this. It's really a transformation of cohomology theories. So shouldn't even do that. So let me just not do this. Let me just say complex K theory. The construction is really not that much harder than the construction from here. Okay. The only thing to have in mind is that you, so the key idea is use the fact that this vector bundle. So of course, X, you basically assume, I didn't say anything today about this, but you have to assume some orientability, okay? You have to assume that, let's say, X is stably complex and, relative to this Lie algebra. I said it this morning, exactly, I gave the precise condition. You have to assume that E is complex as well. You have to use the fact that E has an Euler class. Euler class in the K theory, really equivariant K theory of X. Okay. And then, roughly speaking, if you know how to take, if you can implement what I said this morning, which is that given an orbifold, a complex-oriented orbifold, you can produce a class in K theory. Then what you do, you say, oh, that's actually it's not just a class in K theory. There's a push-forward map. Okay? There's a push-forward map in K theory from K theory of X to the K theory of the point. Okay. And normally you would push down some kind of fundamental class. In this case, you would instead push down some Euler class, or the cap product of the Euler class with the fundamental class, and that's what you would do. So it uses, sorry, something like this should have been a G up here. Then I wouldn't have to worry about it. It uses some functorial properties of K theory. Now, this is the only method that I really know for showing that those that at least in some examples this kind of point. Oh, sorry, let me just say what I want to say on the board. So this homomorphism can be used to detect these orbifolds, which is just gamma, the classes in negative degree. Classes gamma and then point and then V and then 0 in negative degree. And you see some nice agreement between algebra. When you do this, you see some nice agreement between algebra and geometry. If you look at my notion of equivalence here, one of the things that it implies, if V has, really Bordism, has any non-trivial gamma invariant subspace, sorry, no, that's not what I meant. If the fixed, this is the fixed subspace, is not equal to 0, then Bordism class is 0. Okay, and the reason is because if if the representation, if this is the gamma fixed subspace, then what you can do is in a cobordism, you can just move this point to here. Okay, in a cobordism. So in a cobordism, you move it there, and now it's away from the 0 locus, and then that's now empty. The 0 object, the 0 class is the empty derived orbifold. Okay. So then there is some consistency in checking that when you take the class, you take the class of some representation of this nature, okay, and if this is non-trivial, then when you apply this homomorphism to it, which is just some kind of, I mean, you could say Todd genus, but it's basically you just take some exterior powers of the representation and then you take the invariant part there, then you will just get 0 as an answer exactly when this is non-trivial. But if this is exactly when this this fixed subspace is non-trivial. But if there's no fixed subspace, like for example, if you take the non-trivial representation of the cyclic group, then you can just see of rank 1, you can just see that you get some class in degree -1. Okay, so these class we know to be non-zero, and that's essentially all that I know, except that this morning I also mentioned the same extension, the same factorization of this Todd genus, same factorization can be obtained for these mythical objects that I've said nothing concrete about, or Morava K theories, and more generally for K and local theories. Okay. So if you replace complex K theory here by one of these more complicated algebraic objects for which we have less concrete description, then again, classically, there is some homomorphism out of the complex cobordism ring, which is valued in these rings. And this morning I asserted that it factors through the orbifold Bordism ring. If the technical word to prove it is something called ambidexterity. So in order to factor through here, you have to use statement of ambidexterity. Sorry, and then but in order to factor through here, you just combine it with the existence of Euler classes. Yes.
What is the n of, if you take n Morava K theory?
Yeah.
Where does n stop theory?
I mean, I would say everywhere. So what I'm trying to say, so let's say the nth Morava K theory. This is your notation for it. Yeah. So for every n, you expect. So this is the case n equals 1, and for every n, there is a transformation of cohomology theories like this. And you know, if you compose it, precompose it with these things, you will get the usual complex orientation of Morava K theory. If you want to say it like that, if you want to use that language, the usual complex orientation of Morava K theory factors through this. And I just want to say, I don't have time to say much more. Keywords here is ambidexterity. Ambidexterity. Yes. And Euler classes. So ambidexterity is the statement. So what is ambidexterity? So this is some piece of classical piece of, well, classical, no, semi-classical. Anyway, of homotopy theory. It's the key computation is due to Wilson, and then the formulation in this language is due to I think Greenlease and Sadowski. And then the use of the word ambidexterity, I don't know, maybe it's due to Hopkins, something like that. But the theorems that we use are just here. Okay. And what it says is, this says that it says that for a finite group, gamma, the classifying space B gamma, Borel construction satisfies Poincaré duality with respect to Kn. Okay. As far as I'm concerned, I mean, I've been asking the modern experts about it, and there still doesn't seem to be a very conceptual reason for it. As in, you can take this notion and you can abstract it and say, well, it means homotopy limits, finite limits, and co-limits, whatever. You can just take some very abstract notion and say it happens in this case, and it happens in some other abstract contexts. Fine, but the question is, why does it happen in this case? What is the conceptual reason why Poincare duality holds in this case? I don't think anybody really knows. The way this is proved is you prove it for a cyclic group of order P using the presentation as S infinity modulo, using the using the presentation as a circle bundle. Really use it as maps to S infinity over S1, which is CP infinity, and this is the infinite length space. Okay, you just use the Gisin sequence to compute the Moravec theory of this. Okay, and then you see that it is finite dimensional over this ring, and
using the fact that K of n of BG is free.
Yeah. You do some explicit computation. It gives you this fact, and then you induct up the Leray spectral sequence. Okay. I mean, I wouldn't be able to do the induction correctly, but that is what Wilson does. Okay. So once you have this fact, everything else just follows formally. Why this fact holds, I don't understand why it holds. I mean, it holds. I can compute it, but it's some kind of non-trivial fact. So, okay, so that's it, and I really should stop. And the last thing, the really last thing that I want to say is that the split conjecture the map from orbifold Bordism to derive orbifold Bordism splits as a map of spectrum. Okay, so this would be, I would say, other than these, this would be to me the first kind of global result. Some non-trivial. You'll be extracting a non-trivial piece out of the spectrum. The conjecture proof is more or less what I described this morning, combined with this idea of Fukaya Ono of taking some perturbations. It would be very, very, very geometric proof. I've asked around the homotopy theorists to see whether they think they can produce a non-geometric proof, but I think my personal perspective is that homotopy theory may be useful for understanding whether it is possible to produce, whether there are obstructions to producing splittings as maps of rings, as maps of commutative rings, and so on and so forth. Because producing a splitting in terms of spectra is usually very, very hard to do from purely homotopical considerations. Okay, thank you very much.